Welcome to this half-an-hour presentation on sustainable land and water management. A number of institutions are actually using that term land and water management, even though in land the water is already included. Per definition, land is water, soil, vegetation, and animals. But they want to emphasize the water management together with the land management. So we will first look at it in terms of a local example on water management and a second one on water harvesting. Or we could also say it in a different way. It's managing the green and the blue water. Now, what is green and blue water? If you have a rainfall here of call that 100%, it goes into the ground, into the soil, comes up again in the landscape by evaporation, transpiration. 56% of that rainfall water is actually used for the landscape here. Transpiration, evaporation. Another 4.5% for rain-fed agriculture. The rest, 40% remaining, is going into the blue water. Actually, here we should show the groundwater, that is also blue water. And then taken out, coming out by springs for irrigation use. And in the end, 36% of the rainfall are going to the ocean. So the green water, soil moisture, you cannot see yet, but it's very productive, very important, 60%. This water, we will deal with it in the following lecture, the rivers, wetland, lakes, groundwater. Good. Degradation types. 4 types that we see here are dedicated to soils. That shows a bit the emphasis on soil, the bias maybe also on soil. Soil erosion by water, erosion by wind, chemical deterioration, physical deterioration. But we emphasize that there are 2 more. There's biological degradation, the reduction of vegetation cover, for instance, loss of habitats, increase of pests and diseases. Or the water degradation, change of the water quantity of the surface water, decline of the surface water quality would be a second one. So both change in the quantity and change in the quality. We're going to emphasize on this one. Let's look at the water part. We have here 6 types of water degradation. The first one is aridification, a soil moisture problem. Decrease of average soil moisture content. What does that mean? If we have a certain situation and we know so and so much water would be in the soil, and then we realize we're losing more and more soil water, that's the part. A bit difficult to understand. I'm going to explain this further. Then the other parts are now on the blue water. Change on the quantity of the surface water, change of the flow regime, higher peak flows, for instance. The low flows are disappearing. I'm going to deal with that in the next lecture. The same one as well, if you change the groundwater aquifer. We will come to that later. And then you see 2 dedicated to the water quality. One the surface water and the other one groundwater. I'm not going to address this. And also not that the reduction of the buffering capacity of wetlands. Let's look at the first one, that soil moisture problem. What does it mean? To me, this is a very crucial process that is happening here. A certain amount of rainfall falls on the ground. Now, where does it go? One possibility, runoff. That's the amount here going on the surface, causing soil erosion. The second one, going into the soil water. You already might have some soil water in it. So there's a certain amount that is added till your soil water storage capacity is filled up. And then from then on, the water percolates and it goes deeper till it reaches the groundwater. So Basically, what we can say, runoff, precipitation, rainfall, precipitation equals runoff plus the change of the soil water plus the change in the groundwater. And now, out of the soil water, you reduce, you take also out that part that goes into transpiration by the plants. That's the productive part. And evaporation is not productive. It goes from the surface, from the soil, and it doesn't give us any production. So if you look at this, that's the equation, very important. Now let us focus a bit on the possible losses indicated in red. Runoff is one, and the other one is direct evaporation. How do we manage these two in order to optimize the rainfall water, rain-fed agriculture? Here examples. On the left-hand side, a local deep tillage, 25 centimeters tilt, no surface protection, no cover. You see the production here. Next one, right next to it, same soil types, same amount of rainfall, same slopes, 5 to 8% slope. Mulching, a bit of residues, about 50%, and no tillage. Here, direct planting into that soft material. That's when you're planting the next crop of maize. You see the cobs here, 3 times more production than here. And then the same system as mulching, but now combined with trees, agroforestry system, windbreak shade that you can use, and also providing mulch material. Let us look at the first two ones, what it means in terms of the soil water problem. Two places we're looking at. One is in the semi-arid to semi-humid zone, and the other one is definitively in the semi-arid zone, drier place. Now, when we ask ourselves, out of the 100% of rainwater that we get, how much would you say goes to runoff loss? 8%. I'm quite sure you would have guessed more. That's average over the whole growing season. In strong rainfall events, you can have 20, 30%, 40% of the rainfall that flows away. But over the whole growing period, 8%. Now, what is the next? 56% is going to evaporation. Direct loss from the soil surface, unproductive. We're remaining with a bit more than a quarter of that precious rainfall in the semi-arid, in the drylands. 1/4 of the rainfall that we've used for production. If you go to the drier area, what do you think it'll be? Runoff reduced less, evaporation increased. We're having less than 1/5 available for production. If you now say, okay, let's apply mulch, the situation we've seen, we're reducing the water loss by evaporation tremendously, also a bit the runoff, there's hardly any runoff happening here. So we have more than half of the rainfall available now for production. And if you go to the drier place, no runoff, we could almost reduce it to the same amount, but still we have lost a bit more than in the semi-arid to semi-humid environment. So, and the further we go to drier areas, the higher is our loss. So the more into the drylands, the higher is this evaporation loss. The lower the water use efficiency for our production. This is a bit shocking. You see the runoff, everybody's concerned about it, but the evaporation loss, and we measured it over years in different experiments, that was shocking. But you can reduce it. One is mulch, the other one would be windbreak, shade, and so on. Good. I cannot go into more details. Large evaporation losses, not perceived, not seen. mulch systems can even be improved as a conclusion to this one. Then you have some recommendations coming out where you say, oh, let us stop the water erosion, the soil erosion, the flowing away, the runoff of the water, and put ridges, the slope is in that direction, put ridges or furrows here, and then we'll stop erosion and runoff. But you increase evaporation. You've seen runoff is not so high in that environment here, but evaporation. That experiment, which was a recommendation over a period of time, we tried it out. It was worse than any other experiments that we did on different management practices because you increase the surface, the evaporation loss. Actually, this maize here died later on. It was not able to grow up. Good. Okay. That is something that is taken care of with this system called conservation, CA, conservation agriculture, for all kinds of different farmers. There's a big movement going on. A hand seeder here, using all of them using the same principles. The first one is permanent soil cover. You can see that. Minimum soil disturbance. All of them. You seed in directly, also this one here. No plowing, this is the seeder already. And the third one would be crop rotation, which you can't see on these pictures. So you have a whole variety from a few $10 worth equipment here for small scale farmers to animal drawn equipment here that you have to that more than $250,000 machine here, which has a sprayer in front that detects automatically some of the remaining weeds here, sprays them, and behind it puts the seeds into the ground without any plowing. That machine is precision agriculture. It goes by itself, 2 centimeters accuracy. The driver is just here to control whether everything is okay. So you have that whole variety. Now, what are the pros? I point them out. We reduce water loss by surface runoff, also reduce erosion, improve the yields in dry areas because you reduce the evaporation loss as well. And actually, it needs less work than the conventional land preparation. But there are some cons. The herbicides, the contamination. It's getting the discussion about the herbicides is growing at the moment, more and more. Some years back, it wasn't such a big issue, but now it gets bigger and bigger. The other one is maybe that one is using in combination with these big machines also gene technology, as well as new machinery that is needed. So people might have other machines that are for plowing. They don't have this equipment. So you have to reinvest into new machinery. And the last one, not to neglect, is tradition. Lots of people are used. The father has done it, the grandfather. Plowing is an issue. So good plowing is a good farmer. Okay. Now, learning from innovators. If you want to find out what is happening, this is a nice example. We learned a lot from this Alice Gatia, you see already many years back. She had a system fully in place because she was alone with the children. She could not cultivate the conventional way the land and do all the digging. She had to plant directly into these residues. So she did this minimum tillage, she had mulching, she did intercropping with maize, beans, and she already had the trees here, an agroforestry system. So an ideal combination that these days it's called conservation agriculture with trees, which is basically managing green water. But this lady had it all intact already many years back before this big movement came. So we installed equipment, the experiments that we've shown you before, she was part of this setup to try to prove what is happening, where is the water going. Okay, agroforestry, you might hear of it, or I might have heard of it. Grevillea robusta in Eastern Africa, for instance, is a very nice example. It's a great tree for timber, shade, mulch, windbreak. It is not nitrogen fixing. It's coming from Australia, but it's very, very liked in Eastern Africa, all over the place, especially for shade, mulch, and windbreak, and also for timber. A second one is this Phytebia albida, very famous because it has what is called a reverse phenology. During the rainy season, when all the other plants are getting green, that tree drops all the leaves, including the pods, on the ground. So it makes a nice cover. It also is kind of like a nutrient pump. It takes it from the tip, from the ground, and then drops the leaves. So underneath the tree, you get a better yield of maize than away. Usually trees and crops, they are in competition. And that's the way the tree looks in the dry season, full in green. The animals like it as well. They can now go into the shade underneath the tree. And again, because the animals are here, they drop their dung here. So the fertility under the tree starts improving, getting better and better. These are just two examples to show you this potential of agroforestry. There are many all over the world. We could have several lectures on that. But now let's look at these two water losses. The one, the visible one, that is really causing problems as well with erosion. We'll look at that later on. And the other one is then that this one is getting attention. This one has not been getting attention, has been neglected. It's the only time I managed to make a picture out of that invisible water loss. Sun shining on the bare ground here, water evaporating, and then a cold air coming in, and then there's condensation going on. So you see how much water is coming out of the ground. In dry lands, this is a crucial water loss. Okay, now let us look at this experiment. I think it's a very nice one. I would like to share that with you. It's from the US, so they talk about 1 inch of rainfall and 2 inches of soils that they're looking at here. And I show you this YouTube here. Before I do this, I have to change something here in the setup of the, otherwise it will not come nicely. Share, okay. Now, let me hope this works. It isn't again. Okay.
Back to the rainfall simulation unit here. What we have are soil pans packed with soils. These are identical soils taken from within about 3 feet of each other. This pan simulates a natural vegetative cover, thick vegetative cover. The other two on the other extreme, the pan that's been heavily tilled simulates heavily tilled soil, and something intermediate, soil that has been tilled but it has a residue cover on it. And we're going to look at ideally the differences in amount of under our simulated rainfall, amount of runoff and amount of infiltration and flow through into the soils, simulating soil water storage and availability for plant uptake later on. And additionally, if you look at these pans, they're about 2 inches thick, and the ideal soil would have about 50% pore space. So with a 50% pore space in a 2-inch pan, you would think 1 inch simulated rainfall would totally saturate that soil, and you would start to see flow through if every drop of water went into the soil. So what we're going to do is, in a minute, we're going to turn the rainfall simulator on, and we're going to watch, and when we get about 1 inch of simulated rainfall on there, we're going to cut it off and look at the results.
1 inch, open video is 25 minutes. 2 inches, okay. That's about 1 inch.
What you're looking at is the difference between, again, tilling your soil and what people think is loosening it up to improve infiltration, keeping residue on the surface, which you may do with undercutting tools. There may be some tillage involved, but again, you allow some residue to remain on the surface. And what we're doing here is simulating, say, a cover crop that you're planting during the winter, or again, during the growing season, or right before, right after your cash crop. What's happened here, if you look at the jars, and again, we'll take them off for you, is that the majority of the water that we've applied is runoff of the field. Very little infiltration has occurred, and most of the water that's being applied either by rainfall or through your irrigation system is being lost. Not only are you losing water that you're applying, but you're also losing topsoil. The precious topsoil that you're trying to build is being lost along with all the nutrients. The nutrients and organic matter that's being built up in that surface few inches is being lost to nearby waterways. And I can't say this enough, but water quality is probably the #1 resource concern right now that the Ag Center as well as NRCS is dealing with across the country. So just know that it's very important for you to keep that topsoil, that organic matter, and those nutrients on your operation. You can see just by leaving a little bit of residue that we have quite a bit more infiltration. You can see the difference between bare soil and just a little bit of surface residue. What that surface residue is doing is protecting the soil and again dissipating that energy from the raindrop, allowing it to slowly infiltrate into the soil. And those very small particles, instead of being dislodged and blinding off those pore spaces that allow infiltration, it's allowing the water to slowly infiltrate. And again, you do have some infiltration. This is kind of a in between, or I mean, it's okay, but it could be better. And you can see there is some flow through into the system. This is water that you're banking for later on, and this is your water storage capacity. And you can see the best system is again to keep a living root growing throughout the year. And the best way to do that, in addition to obviously growing your cash crops, is to plant cover crops. And cover crops will not only help you improve infiltration year-round, but they'll also help you build organic matter. And it's organic matter that's responsible for holding the soil structure in place, keeping it intact, and maintaining that water holding capacity that's so important for, again, taking advantage of irrigation water that you apply or Mother Nature's rainwater.
Okay, this is a very nice experiment that shows the crucial process of splitting up rainfall into runoff or infiltration. You have the link here, you can have a look at it yourself. Okay, now let's look at this one here. Cover is so important, also pointed out, from 0 to 50% cover. Now let's look at the percentage of runoff that you get from different rainfall events, 10 millimeters, 10 to 20 millimeters, and more than 20 millimeters. So the higher rainfalls here, more than 20 millimeters, they give more percentage runoff here. You can see they can go quite high if you don't have any cover. So the moment you get into cover conditions, 10%, 20%, 20%, you've reduced it almost to half here, if you look at this coming down for the highest rainfall events. So if you now look at it, the same situation now, the same experiments cover here, 0 to 50%, soil losses. You see that the soil losses are concentrated on this side, below 10%, 12%. That's when cover, we get then the highest soil loss. We still get the runoff here, water is still flowing, but the soil is held intact because you have some cover on the ground. And that is exactly what we will use in the next one that I'm looking at. That's now the rainfall runoff harvesting that we're looking at. So basically we have different principles here. We can reduce soil evaporation, that's the green water, we've looked at that. Retain runoff, avoid any runoff, that's green water management. The moment we go to this one, trap runoff, water harvesting systems, then we're looking already at the management of the blue water. you have these basic principles. You can divert it, get it, the extra water, get it away. You can impede it, slow it down, or you can trap it. These parts we will look at next time. I'm now looking at this water harvesting. So basically for water harvesting, you have always three different areas. One is a catchment area. That's where you collect the water. That's where runoff is happening. We could be having a conveyance system. Then you have a storage place here. Here it's an open dam, here open water dam. And then you have an area application for application. These three systems, you can have it all also in a few meters distance. So here the water is running away, runoff, and getting into that area. You store it here, that's in the soil, you have your water storage. And then from here you use it. You plant your trees or crops here. So here a few meters distance, it's in the field, and here it's a regional, it's a landscape system. All these practices are very nicely documented in that book that we put together a few years ago with a number of different partners worldwide. You can have a look at it and you see it well illustrated. So the first system we would like to look at is this runoff from rooftops that we are harvesting, or from courtyards. We are harvesting that in tanks here. This is what is called rooftop or courtyard water harvesting system. It's a local system. The second one, also a small system, micro catchments, a few meters from one place to the other one. Here, this system here is called SAI in Western Africa. Holes that you dig and you plant in the cereals, the sorghum here together with some manure. You concentrate the water, you collect the water from nearby areas that are rather bare, and you focus or you concentrate it on these plots here, and here you have production. The same system here, a bit further away, but trenches here that collect the water that is flowing. Here it stops the water flow, the next one starts again. These are small applications, this one here even with a green green strip here that collects the water and slows it down, has better infiltration. So here you have more water available for that green part here. So these systems have a ratio from the catchment to the application area of 1:1 or till 10 to 1. Then you get to the bigger ones, but the storage is in the soil. You get to the bigger systems like this one here, where you harvest in that area here, you collect the water, and then it is going into a surface dam. You recharge the groundwater table, and in this system here, for instance, you take it out again, that groundwater, and use it for irrigation. So this is blue water management here. And here the ratio between catchment and application area is between 10 to 1 till 100 to 1 or even more. So these are big systems, and the next one is even bigger, but this one here is storing the water above and below ground. The next one here, flood water harvesting, it captures excess water from far away, there are floods, it's in exceptional years and rainfall events, and then spreads it on the land, and you actually store the water mostly in the soil here. You use a vast areas where you store the water in the soil, and then you use it for production. This is the flood water harvesting system. Okay, and here you store the water now below ground again in the soil. You can see water flowing this side, and the structure here that stops the water from being channeled, it spreads it over the land, and then you can use that area for crop production after the flood. Here you have an overview of the 4 groups of water harvesting systems. The largest one, flood water, macro catchment, micro catchment, and the rooftop courtyard water harvesting. These systems have gained and are still gaining more and more attention because there is lots of water loss by runoff that can be used with these water harvesting systems. You can have a good look at it. It's well documented. I've given you the contact for the book that we produced. I hope you enjoy having a closer look at these ones. So we come to the end of this lecture here. I try to show you the green water management, some parts of it, how we can reduce the evaporation loss, the runoff loss. These are two basic principles. And I showed you something on trapping runoff harvesting systems that we had a look at. For the next time, we will look at the bigger systems. What is going to happen about and what impacts does it have if you have a lot of water flowing downstream and causing floods or disasters? We will have a look at that one. How can we make best use of the rainwater upstream and make best benefits for the people downstream? What are the on and off-site benefits of sustainable land management? I wish you all the best and hope to see you in 1 week's time.